Hi everyone. So in this video we're going to tackle a beam problem that has non-classical boundary conditions, also known as mixed boundary conditions. And what we have here is a cantilevered beam that at its tip we have a discrete mass and a spring. Let's give these some coordinates. We have the axial direction, which is the x-axis, and the displacement along that axis is u. And then in the transverse direction we have the z-axis with displacement w in that direction. The length of the beam from root to tip is L, and we would assume that this is a uniform beam so that M and EI are constant along the length of the beam. And then we have this discrete mass at the tip. We'll call the mass of it M and the moment of inertia I sub M. The spring has a stiffness of K, and for good measure we'll add a compressive load at the tip, which we'll call P. Notice that P is in the negative x direction. Okay, so as always, we start off by writing out Hamilton's principle that the integral from t1 to t2 of del t minus del u plus del w sub e dt is equal to 0. That's equation 1. So first, let's find the expression for the kinetic energy, T, and we'll adhere to our color coding and do this in green. T is equal to the integral from 0 to L. This is just a half mass times velocity squared. So it's 1/2 the mass m times the velocity w dot squared dx. I should mention that this m here is a mass per unit length, while this m here is just a mass. It's a discrete mass at the tip. So we need to integrate this along the length of the beam. Plus, we need to add the effects of the mass at the tip. That's 1/2 m times the velocity of the tip squared, which is w dot at L squared. Plus we need to account for the rotational kinetic energy of this discrete mass. So that is plus 1/2 I sub m times the rotational velocity at the tip, which is just w comma x dot at L squared. So using this expression, we can find the variation of the kinetic energy. Del t is equal to, since the mass is constant, I can take it outside of the integral, and we get m times the integral from 0 to L. The 2 cancels the half, and I'm left with w dot del w dot dx. Taking the variation of the second term, again the half cancels with the 2, and I'm left with m w dot at L del w dot at L. Taking the variation of the third term gives me I sub m w comma x dot at L times del w comma x dot at L. And some numbers, number 2 and 3. And that's it. That's the expression for the variation of the kinetic energy. Similarly, we find an expression for the potential energy of the system, U. The first component of this is the strain energy of the beam. It's 1/2 the integral from 0 to L of EI w comma xx squared dx. And we need to add to that the contribution to the potential energy that the spring gives us, 1/2 K times the deflection of the spring squared. And since the spring is at the tip, its deflection is just W of L squared. So we can take the variation of U. This implies that del U is equal to, since EI is constant because it's a uniform beam, I can take that outside of the integral, and I'm left with the integral from 0 to L. The 2 cancels the half, w comma xx del w comma xx dx. Plus the contribution from the spring, again the 2 cancels the half, and I'm left with k w at L del w at L. And let me just draw a line here. I'd like to get the external work on the same page for convenience. The external work is a result of this load P acting on the foreshortening displacement. As the beam bends, the tip of the beam will move in the negative x direction. We've seen this in a previous problem. And the external work, which is the foreshortening work, can be written as P, which is just constant, times the foreshortening displacement, which is 1/2 the integral from 0 to L of w comma x squared dx. Taking the variation of this gives us del WE is equal to, P is just a constant, integral from 0 to L, again the 2 cancels the half, and we're left with w comma x del w comma x dx. Let's give these some numbers, 4, 5, 6, and 7. All right, so let's go and tackle Hamilton's principle by parts. Since this is really lengthy, we'll deal with each one of the individual components separately. So, integrating from T1 to T2, the variation of the external work, dt, is equal to the integral from T1 to T2 of, and then I'm just going to substitute equation 7 in there. So P times the integral from 0 to L of w comma x del w comma x dx. And we need a dt. What do we need to do next? We recognize that this del w comma x needs to be del w, and so we need to remove that derivative. How do we do that? Everyone? All at once? Integration by parts. Okay. The integral from T1 to T2 of delta we dt is therefore the integral from T1 to T2 of, now remember what we're going to do. We're going to take this part as the boundary term and just remove the derivative from the del w. So that gives us P w comma x del w. That's evaluated at 0 and L. Then minus, very important, the minus sign. We take the integral, but we put an extra derivative on the w comma x. So, minus the integral from 0 to L of, can take the p out since it's constant, w comma x, x, second derivative, del w dx, and I need a dt. That's it. That is the expression for the variation of the external work, and we'll call that number 8 and put a yellow box around it, since we're going to use this later. We proceed in a similar fashion with the strain energy or the potential energy. The integral from T1 to T2 del U dt is equal to the integral from T1 to T2, and then again, just from the previous page, equation 5, just going to substitute that in. And I need to close off with a dt. And that is equal to, again, we're going to integrate this term by parts, but we've got to do it twice because we have a second derivative. This term, I should mention, does not have to be treated at all because the variation of w has no derivative there. All right, so again, we get the integral from T1 to T2. We're going to take this expression, evaluate it at the boundaries, but we're going to drop one of the x's from the del w comma xx. That gives us ei w comma xx del w comma x at 0 and L. Flip the sign to a negative. We got negative, the integral from 0 to L. And what we do here is we add a derivative to the w comma xx. So I can take ei out since it's constant. W comma xx, x, third derivative. Del w comma x dx. And then the contribution from the spring remains unchanged. Close brackets dt. Now we've got to go through this one more time because we've got to integrate this by parts to get rid of the derivative here on the del w comma x. So the integral from T1 to T2 of del u dt is equal to the integral from T1 to T2 of, I'm just copying the boundary term, that remains unchanged, minus, help me out here guys, what does the boundary term look like from this? Minus, because of the minus sign. I'm going to just remove that derivative from the del w comma x. So I get minus ei w comma xxx del w evaluated at 0 and L. Flip the sign again so it becomes positive again. The integral from 0 to L, and all I'm going to do is take this expression here, but add a derivative to this part. So ei is constant times w comma xxxx, the fourth derivative of w with respect to x, times del w dx, plus the spring contribution again remains unchanged. Close brackets dt. And that is the expression for integrating the strain energy between times T1 and T2. Let's give it a number 9 we're up to, and put a yellow box around that because we're going to need that later. All right, so let's continue on the next page with the variation of the kinetic energy. So the integral from T1 to T2 of del T dt is equal to integral from T1 to T2 of, then we're just going to substitute equation 3 in there. I'm just going to paste it all in there, dt. Okay, so the next step, what I'm going to do is just break this up into two separate integrals. I'm going to separate the one term that has the integral from 0 to L from the rest. So this can be written as the integral from t1 to t2 of this first term, dx dt, and then separately the rest of it, plus the integral from t1 to t2 of the rest of it, dt. Okay, no great mystery there. What do we need to do next? We need to flip the order of the integration here. So we'll just write that as the integral from 0 to L of m times the integral of t1 to t2, w dot del w dot dt dx. Plus, then the rest of it remains the same. Okay, so notice now that we have a del w dot here, a del w dot here, and a del w comma x dot here. So we need to integrate all three of these terms by parts in order to get rid of the dot on the del w dot. Remember that because this is kinetic energy, we're now integrating with respect to time and not with respect to length. But the rules are all the same. This is equal to the integral from 0 to L of, now we've got to put the boundary term down, which is just this with the dot removed from the del w dot. So m w dot del w evaluated at t1 and t2. And I remind you that if we go back to the definition of Hamilton's principle, since the state is known at both time 1 and time 2, the variation of w is 0 at both these times. If you've forgotten why that is, there's a link up above to the video in which we derived Hamilton's principle, and I've explained it there. Hamilton's principle fundamentally says that in moving from time 1 to time 2, the system follows a path that minimizes its Lagrangian. But it is assumed that the state of the system is known at both time 1 and time 2, and we're using Hamilton's principle to find the state of the system in between those times. Okay, so minus, and then it's just this part where we've moved the dot to the w dot. Okay, so minus m times the integral from t1 to t2 of w double dot del w dt. And then we need a dx. Okay. Similarly, we need to treat these two terms the same way, and I'm going to do them together. First, the boundary terms of each. Remember the boundary terms, we just get rid of these dots on the del w's. So this is equal to plus m w dot at L del w at L from t1 to t2. And then for the same reasons, del w at L is 0 at both time 1 and time 2, since the state of the system is known. Therefore, the variation is 0. Similarly, for the second boundary term, we get im w comma x dot at L del w comma x at L. Again, these are evaluated at time 1 and time 2. And just so there's no confusion, I know I've used a bit of shorthand, but w, even though I'm evaluating it at L, is a function of both x and time. I've just left out the time dependency for shorthand. But don't forget that w is both a function of x and of t. So we'll mark that as 0. And then we've got to subtract, flip the sign, subtract the integral from t1 to t2 of, and then it's just these two terms, but where we've moved the dot across, right? That's the way this works. So that's equal to m w double dot at L del w at L plus im w comma x double dot at L del w comma x at L dt. Okay, so we can simplify this by removing the boundary terms, all of which is 0. This is equal to the integral from 0 to L, and all I'm doing is I'm copying this term and I'm copying these two terms. No magic here. Minus the rest of it, dt. Okay, so I just took this expression in the line above and I cancelled the boundary terms that was 0, and what remains is the rest of it. Okay, and I can't quite fit it on one page. I'm going to have to finish it on the next page. The last thing that needs to be done is to switch the order of integration here. So, continuing on the next page, the integral from t1 to t2 of del t dt is equal to the integral from t1 to t2, flipping the order, and I'm going to group everything under this one integral from t1 to t2. So, minus m times the integral from 0 to L of w double dot del w dx, and then minus the two boundary terms. Minus mw double dot at L del w at L minus I sub m w comma x double dot at L del w comma x at L. And close brackets dt. Okay, and this is it. This is the expression for the variation of the kinetic energy. integrated between times t1 and t2. Let's give it a number. We're up to number 10 and a yellow box around it. Now we can use our expressions for the variations of the kinetic energy, potential energy, and external work, and simply substitute them into Hamilton's principle. Now I'm going to keep the color coding intact so that you can see the contribution of each. So Hamilton's principle gives us the integral from t1 to t2 of the variation of the kinetic energy. I'm just going to paste it in. This is the expression above, number 10. And then minus, because according to Hamilton's principle, we subtract the variation of the potential energy. Minus, then everything in blue is what I got from equation 9, except that I've distributed the minus sign across each of the terms, plus the contribution from the variation of the external work, and that I'll put in red. Close brackets dt, and of course all of that is equal to 0. We'll number this number 11. Okay, and we are basically done. The only thing that remains to be done is to group the corresponding terms. So the first thing we'll do is we'll group all the terms together that involve the integral over L. That gives us the integral from t1 to t2 of, and I'll use purple for this, integral from 0 to L of, and then from each of the contributions, minus mw double dot, minus eiw comma xxxx, minus pw comma xx. Close bracket, del w dx. Next we'll list the boundary terms, but what I'll try to do is keep the ones that involve del w together, and the ones that involve del w comma x, I'll keep those together. So minus mw double dot at L, del w at L, plus eiw comma xxx del w at 0 and L. By the way, for this boundary term, I've just evaluated it at L. The reason for that is this discrete mass and the spring only appear at L, at x equals L. They don't appear at the x equals 0 boundary. I suppose I could have written it like this with L and no lower limits, but I don't want to confuse you. These are all boundary terms as if I had written it that way. Okay, and we're going to add to this the spring contribution minus kw at L del w at L. And I've got one more plus pw comma x del w at 0 and L. What I've tried to do is keep together the boundary terms that all involve multiplying by del w. And then lastly, the boundary terms that involve del w comma x. So minus eiw comma xx del w comma x at 0 and L, minus I sub m w comma x double dot at L del w comma x at L. And of course all of that is equal to 0 still. We'll call this equation 12. All right, so now we're basically done. We have everything that we need substituted into Hamilton's principle, and that will conveniently now give us our equations of motion plus our boundary conditions. And I remind you that in order to satisfy this equal to 0, each of these groups of terms need to go to 0 independently. So everything under the integral needs to go to 0, and independently all the boundary terms that multiply del w need to go to 0, and independently again the boundary terms that multiply del w comma x need to be 0. Starting off with the equations of motion, we invoke the fundamental lemma of the calculus of variations, which tells us that because del w is arbitrary, therefore everything multiplying del w must be 0. Okay, so the equation of motion is that minus mw double dot minus eiw comma xxxx minus pw comma xx is equal to 0. Now obviously, since each term is negative, I can multiply each of them by minus 1, and in doing so just flip the signs of each. And so the signs become positive. We'll call this number 13. Now let's take a look at the boundary conditions. Well, first of all, let's look at the ones at x equals 0, because these are pretty straightforward. They are, of course, both geometric boundary conditions. And since it's built in at the root, we know that the displacement w of 0 is equal to 0. This implies that the variation del w at 0 is also equal to 0. And similarly, the slope w comma x at 0 is equal to 0, which implies that del w comma x at 0 is equal to 0 too. Let's put some red boxes around these because these are final results, and number 14 and 15. All right, and now for the more interesting boundary, that's at x equals L. we have the so-called natural boundary conditions there. They're called natural boundary conditions because they naturally come out of Hamilton's principle, although I prefer to call them forced boundary conditions, but most of the texts refer to them as natural. Okay, so because of what I've written here, namely that del W and del W comma x are 0 at x equals 0, I can effectively ignore all the lower limits of my boundary terms because we've dealt with those. I just need to consider the boundary at x equals L. Okay, so the first thing I'm going to look at are these four terms here, and all of those multiply del W at L. So I have minus m w double dot at L plus eiw comma xxx minus kw at L plus pw comma x times del W at L must equal 0. Now let me just say, these were the terms that I had initially that came out of the problem setup, and that's why I've got the L in there. But since we are evaluating it at x equals L, I don't really need to explicitly include the L in there. These other two terms don't have the L in there because those are the boundary terms that came out of the integration by parts. And I didn't explicitly put an L in there because initially we were going to evaluate those at each of the two boundaries. So because we don't know del W at L, del W at L cannot be assumed to be 0. It should be assumed to be arbitrary. Therefore, everything multiplying that must be 0. So minus m w double dot plus eiw comma xxx minus kw plus pw comma x. Notice I've dropped the explicit x equals L from that, since we have it here. But all of that added together must equal 0. Let's put a red box around that, because that is now our third boundary condition. Then the final boundary condition will come from these two terms, evaluating it at x equals L. So minus eiw comma xx minus I sub m w comma x double dot at L times del W comma x at L is equal to 0. Again, since we're evaluating this at x equals L, we can drop this explicit dependency on L. And since we know that the slope at x equals L is not necessarily 0, we need to assume it's arbitrary. Therefore, it might not be 0, in which case what multiplies that must be 0. So, and I can flip the signs on each of them, eiw comma xx plus I sub m w comma x double dot is equal to 0. Red box around that, and we're done. We're just missing a couple of numbers, 16 and 17. And that's it, we're done. 16 and 17 are known as natural or forced boundary conditions. Okay, and before we go, we're going to take it from the top one more time. We have a uniform beam that is cantilevered at the root, and at the tip we have a discrete mass plus a spring plus this applied compressive load. We of course want to apply Hamilton's principle. We derive expressions for the variation of the kinetic, potential energies, and the work. That's what I do over the next few pages. Then we plug all of this into Hamilton's principle, which I have over here. Then I group them so that everything under the integral from 0 to L is together, and that the various boundary terms are together based on the variational quantity that they include. We then make the point that each of these groups of terms has to go to 0 separately. What is under the integral becomes the equation of motion, and then the boundary terms allow us to find out what's going on at each of the four boundaries. In the case of the x equals 0 boundary, those are geometric conditions that we know well. And then at the other two boundaries, at x equals L, we come up with an expression that must be 0 in order to satisfy Hamilton's principle. The reason we come up with this expression is we know that what it multiplies is non-zero. Okay, and with that, we are done with this video. I hope you guys found something useful and interesting in it. If you did, please go ahead and smash those like buttons. It really helps in getting this video in front of other people like you who might want to see it. If you would like to be notified of future video releases, please hit the subscribe button below and click on the bell icon. As always, the notes for this video are downloadable from the link in the video description. If you have any questions, comments, criticisms for me, feel like you didn't get value for money, I'd like to hear from you in the comments below. Thank you for watching, and I will catch up with you in the next one.